Co to vlastně děláš?
Takže já tady mám vzorky z fermentace a tady ty vzorky dávám do NMR kyvet, který potom budeme měřit teda na NMRu. Důležitý je, že ty vzorky mají v sobě NMR buffer, který obsahuje standard TSP, se kterým se potom budou ty analyzované látky srovnávat. A zároveň jsou ty vzorky centrifugované, aby byly čistý. A my vlastně z těch centrifugovaných vzorků odebíráme tu čirou část a dáváme je do NMR kyvet, aby jsme je potom změřili.
Dobře, takže pokud tomu rozumím správně, tak ty jsi měla tady nějaký experiment, proběhla fermentace a ty vzorky, co jsou zfermentované, tak jsou tady v těch zelených,
jo,
vlastně
tak.
už předcentrifugované a všechno.
Přesně tak.
A teď momentálně pipetuješ vlastně z těch vzorků do těch kyvet, tak co to kyvety, že ano?
Přesně tak, takže já vlastně pipetuju tady to už centrifugovaný, ten centrifugovaný vzorek, pipetuju to tak, aby se mi tam nedostal ten kal, který je ve spod. A dávám to do NMR kyvet, který bych se měla dotýkat jenom nahoře, aby se ta část, protože oni se měří vlastně vždycky tady v té části,
jaký,
tak
to
vlastně takhle, té spodní části, tak aby to bylo čistý.
Hele, skvělý. A kolik tak se tam toho dává? Tak 1 ml, půl mililitru?
Dáváme tam 600
mikrolitrů. Jo. Aha. Takže teďka si vlastně připravíš takhle všechny ty vzorky a potom je dáš rovnou do NMR?
Přesně tak.
Tak super. Tak se vrátíme za chvilku. No.
Takže vzorky máme v NMR kyvetách a teď je potřebujeme dát do NMR přístroje. Takže máme na to takovou trubičku a vlastně to nám umožňuje, aby vždycky ten vzorek byl vlastně ve stejné výšce a aby se mohl správně změřit. Takže takhle se vlastně dávají vzorky.
Takže ta kyveta se v podstatě dá jenom do toho a vloží se to tam.
Tak, kde je vlastně naznačený, v jaký části se vlastně probíhá to měření a je důležitý, aby vždycky ta kyveta byla ve stejné výšce.
A můžeme se na to podívat ještě jednou na tohle? Na to číslo, tady na tohle?
Jo.
Jestli nevadí.
Jako takhle?
Jo, přesně tak. A teďka mi teda řekni, já vidím tu hladinu někde třeba u 5 nebo i víc.
Jo.
A co to pro mě znamená?
Vlastně prakticky to znamená, že tady v té oblasti ono taky se to měří ne vždycky úplně stejně, ale zhruba tady v té oblasti dochází k tomu měření a tam by rozhodně měla být ta kyveta čistá a měl by tam taky být ten vzorek.
Dobře, takže to měření je vlastně tady v této oblasti a tady nic. Ale je dobré, aby tam něco bylo, protože to bude nasávat. Jo, super.
No, nasávat to nebude.
Jo, to nenasává.
Nenasává. To prostě, to tam jenom... Vlastně tady máme ten autosampler a ten se točí do kolečka a tady v této trubičce tak se ten vzorek dostává dovnitř toho NMR. Dostává se vlastně doprostřed magnetu, kde dochází ke změně spinu jader těch látek a nevím, co jsem chtěla říct.
Tak pořád díky tomu to potom vlastně měříš, že?
Tak a díky tomu se to vlastně změří, přesně tak. Takže vlastně tam nedochází k žádnému nasávání, ale vlastně tady ten vzorek tam jenom zajede a vlastně dorazí do toho magnetického pole a tím se změní ty spiny a může se to změřit.
Jo, takže on tam jenom čistě je a tam je nějaký chlad, že jo, dole.
Jo. Vlastně ten magnet musí být hrozně silný a proto je potřeba chlazení a chladí se to jednak heliem, který je tam neúplně natrvalo, ale mění se jednou za rok nebo tak nějak.
A helium, pokud se nemýlím, je v té láhvi, že?
A ne, to ještě dusík. A ten dusík právě tady v té láhvi.
Takže to je C-dusík.
A ten se mění vlastně jednou týdně.
A helium?
A helium to tam, to je
Vždycky
to v podstatě jakoby trvalé.
Aha.
Nebo mění se to jednou za, já nevím, za pár let, za rok nebo za víc.
Jo. Aha. Tak super. Tak asi teďka pojďme dál. Počítači.
Tak a teď máme teda, tady máme program, který nám umožňuje zadávat parametry toho měření a my si tam vložíme, vždycky si tam vložíme nějaký popisek toho vzorku, takže tady máme, že to je vzorek číslo 841, což my víme, že nějaký dárce 15, jaká je to látka a kolikátá je to hodina. Experiment je to číslo 1. Je to rozpuštěné ve vodě.
A těžké vodě, že jo? To je kombinace jednoduché a těžké, nebo jako klasická těžké?
Tak, takže tady máme nějaké parametry pro to měření. A pak vlastně zadáváme, jakým způsobem se má ten vzorek měřit. Už tady máme
já si to obejdu a podívám se možná z druhé strany, no to bude lepší, ty vědět, co se budou dívat.
Tak.
Aha.
A zadáme si parametry toho měření. Vlastně celý tady ten řádek je vlastně příkazový řádek, který tomu přístroji říká, co má sledovat a jak má ten vzorek měřit. To první číslo je, kde ten vzorek se nachází v autosampleru. Takže teď to máme 21. Tak. A teď už je to vlastně nastavený a tady vidíme, že už předchozí vzorky, které jsme zadali, tak už se měří.
Jo.
A to první měření, vždycky je důležité to první měření, protože tam máme i jiný příkazový řádek, protože tam se vlastně zjišťuje rezonance vody, nebo nastavuje se tam rezonance vody, která se pak používá pro všechny ten zbytek. No, to asi všechno.
Skvělý. Tak jo, takže teďka tam vlastně, teďka musíš tam dopsat ty ostatní, nebo?
Tak, přesně tak, takže teď tam dopíšu ostatní. Takže máme teď tady 842, což je 15, rutin, 8 hodin.
Tak a třeba u HPLC, tak tam se měří ty vzorky v několika opakování. Tady vlastně vy máte taky několik opakování, nebo měříte vlastně ten vzorek čistě jako jednou a několikrát, nebo měříte jenom jeden vzorek?
Měříme jenom jeden vzorek jednou a většinou to bohatě stačí.
Jak dlouho to trvá?
Trvá to, tady v tom případě to trvá 16 minut jeden vzorek.
Aha.
Ale záleží, co se měří. Může to trvat i kratší dobu, nebo i delší dobu. Ale kdybychom chtěli, tak vlastně ten vzorek máme schovaný v těch kyvetách a můžeme si ho vlastně přeměřit znova, kdyby to bylo potřeba.
Jak dlouho se tak skladují? Dokud se neodevzdá článek.
Tak. My už skladujeme asi půl roku vzorky, takže...
Tak a teďka mi jenom řekni, jak je to asi časově náročný, řekněme, teď dneska máme 26 vzorků, jestli jsem tomu rozuměl.
Aha, 24.
24 vzorků, takže vlastně to připravit, nemluvím o té fermentaci, o tom původu, ale o tom to vlastně dát do těch kyvet, jestli tomu rozumím, jestli se to tak jmenuje, a potom do toho stroje a to měření samotný, to trvá?
No, změříme tak vlastně 2x24 vzorků za den.
2x24?
Jo, takže 48 vzorků.
Jezdí to i přes noc?
I přes noc.
Aha.
Někdy se poštěstí měřit jakoby 3 ty sady, ale to je, když jsou na to 2 lidi.
Super. Tak jo, je to ještě něco, co se bude s tím strojem dělat, jestli se bude teďka nějak nasávat nebo? za jak dlouho?
Tady, jo, no zrovna tady máme, že to nevidí úplně za jak dlouho, většinou tady je za jak dlouho to změří, ale já myslím, že teď to bude za těch 10-15 minut, protože si myslím, že před chvílí tam skočil nový.
Jo, jasný, v pohodě, tak to nemusíme nic stavit zbytečně. Já mi tady vysvětlit, tady Manku už vysvětlit, co je. Tady vidím, když se podívám, nějaká teplota 305 Kelvina, potom ta sonda 298 Kelvina, je to tak nebo?
No, ale to je úplně.
Nevadí, OK. Tak jo, díky moc.
Ahoy, I want to show you, this is the NMR machine. NMR is nuclear magnetic resonance. Sure, you see a machine, you see samples, but what's in there? What that really is a very big magnet. That's really what that is. Because each sample, you, me, everything, are little molecules, they are spinning. So what this does, the big magnet makes everything homogeneous, and then you send a pulse of energy which changes the energy state of the molecules very slightly. So they get excited, but once they fall back to their normal state, then that change between excited and normal state, that's what allows us to, that signal allows us to tell the difference of what molecule it may be. Because each one has a very different and unique signature. And like that, we can then guess or assign, depending on our data, what molecule it may be or what chemical group it may belong to. Let me show you a little bit of the computer. So here goes the sample. A sample looks like this, for example. They are usually liquid, and usually, let's say you had a plant, urine, or something else. After the extraction process, you end up with this liquid, which is very little. It's not much. It's only about 500, 600 microliters. It goes in here, and then it will go into this magnet, the NMR machine, and then you will get the results here. A computer, this is the program we use. Let me show you an example of spectra. What we get is spectra. Let me find my name. It's gonna... So I'm just searching through the folders. And for example, here I have one that I did recently. As you can see, the spectra comes out like this. It may look differently. It's gonna look different depending on what sample you have. And of course, when I get this, I need to fix it. Usually, for example, if I do this, as you see, it moves. I want to make sure that I align everything the way I want to. The first signal to the right is my reference. So I already know how it's supposed to look like, so I want this aligned. I don't want them uneven. I want those two little peaks aligned. And after that, I don't want that to move, so I'll do this. Then I'll try to fix the other parts. So here it's okay, but here it's a little uneven, so I can adjust it with this. And later on, I'm gonna use another software to further fix this. But, so once you have this, and once it looks okay, okay is gonna mean different things, but in this case, I know this one is okay. I'll just save it. And then I would transfer this spectra to another computer so we can actually try to assign the different chemicals that may be in our sample. So I would just use a memory stick from the computer and take it to another computer. So let's go to the other computer and get a general idea of how that looks.
Let's go.
And thank you. Here's a seat, and here's my seat. So another computer. Let's find one of the files. There are many programs we use. One we like a lot is called Chenomx. And in Chenomx, you can try to find, try to fit different spectra.
It's just for Bruker or for...
No, this is another brand. Bruker was the machine.
Yeah,
And then these ones are programs that are compatible with the spectra, because we got spectra, so we want to further fix it, because of course, since it's not perfect, you have to align it, make sure that the peaks are clean. And if not, you may have to do a sample again.
Yeah.
So that's why every part of the process is important. It has to be a clean sample. Then you can see, as we just did over there, if the spectra looks good enough. If it is, then we can continue with this. In here, we will do more fixing steps. In here, the data already looks nicer, but for example, if I wanted to correct the baseline is, as the name implies, the line that's the base. You know, the program kind of suggests something, and then I can actually change how it is. Because, for example, if I zoom in here,
Is this cheating?
no. Actually, you want to try to do it as realistic as possible, because each peak, the area under each peak, actually, it's going to tell you an idea of how much of that chemical there is. I mean, here we see many peaks, right? They just seem like, do they mean anything? And they do. We'll see in a few seconds what that means. So this is, I'm not gonna complicate things too much with you here, but there are many tools to align the baseline, fix how wide these things are or not. And as with everything, every step has its pros and cons. You may change something, it may make something clearer, but it may also take away some accuracy, or vice versa.
Yeah.
So you have to play around depending on the quality of your sample, the quality of your spectra, and you will know your data best.
Yeah.
But once everything is good here, this is one section of this software. There's another section, this is the processor.
Yeah.
Then I take this to the profiler. Profiler, as the name implies, we're gonna create a profile of what's there. You see, this is the same spectra, but now you see I have some red peaks.
Yeah.
Those red peaks are the ones that I have been working on and assigning. So what are they? For example, let me go to my list. In here, I have found 48 potential compounds. Some of them I'm very confident about, some of them I'm not. It all depends on your study, but sometimes, let's say you're interested in biotin, for example, and you think you see it, but you're not sure, you may use a standard and run it again through the machine, but that's an extra step. But for example, here, what's something that everybody here has heard about? Let's say methanol.
Yeah.
And by the way, the sample I have here is a human fecal sample. It's a child, actually. But for example, if I look for methanol, the database has it. And let me zoom out of this. As you see, methanol, it highlights something in blue, purple. So I can zoom in there. This one's pretty easy. Methanol only has one peak.
Yeah.
And let's say if I erase it, there's my peak in the black color. If I write methanol, it's, let me do that again. Hold on, I'm doing a mistake here. mean, I'm gonna look for methanol, but I already erased it, so I need to get this fixed. So if I, again, as I told you, let's look for methanol. So I zoom in to where the peaks are.
Yeah.
This one is very easy because it fits right away. See, and I can adjust it. Like, you want to try to get it as close as you can to what it may be. In this case, we just have one peak. If you see here in the name, methanol has only one peak at 3.3.
Yeah. And can you explain these, the x-axis and y-axis?
Yes, the x-axis, it's ppm, parts per million. What's very important to know about this, that in NMR and your spectra, it's only a relative axis. It's not like 2 or 4 mean anything specific. It's not like 4 liters or 4 grams. It's not. It's all based on your reference. Remember when I told you that to the right side there's a peak? That's my reference.
Yeah.
When I ran my sample in the machine, I also added a reference. There exist different ones. Some of the common ones are TSP or TSM. The reference, the size of it, and the shape, every other compound that I find in my spectra, their proportion, like their quantity in the sample, it's gonna be related to its proportion to the reference.
Yeah.
That's why the reference is so important. When I get my spectra, that's one of the things that I need to make sure that it's correct. And also the good thing with the reference is that when I prepare my samples, I know how much of it there was. So that will give me a good idea later on when I try to quantify how much of a compound I have here.
And what about y-axis? Is the same or?
Y-axis
intensity?
would give you the intensity.
Yeah.
And for example, as you see here,
Uh-huh.
there are some very tall peaks. There are some shorter peaks. In everyday language, the higher it is, the more of that compound is there. I showed you methanol, which was pretty easy because it only has one peak, but there are other ones. For example, you may have heard of butyrate. So butyrate, I do have it here. But as you see, remember methanol? It only had one number here, only one peak. This one has 3 peaks. So that's 3 places that you have to worry about to make sure it matches.
Yeah, I see it.
You see this purple 1, 2, 3.
Yeah.
So you could start with 1 because sometimes when you start with something, it may be like this. Like that's way bigger than what you actually have. So you try to fit it to the spectra. The problem is sometimes, for example, in this region, there are many other overlapping peaks. And so it's like, which one is butyrate? Is this butyrate or is this the other compound that's nearby, valerate or something else? Caprylate in this case. So in this case, usually if I have 3 peaks, I try to first start with the peak that is less ambiguous, the one that I'm most sure about. This here, this quadruple peaks, 4 peaks, they seem to be very unique to butyrate. So I would start there because there's less chance that I would be wrong in assigning this peak. And once I assign this peak that I am more sure about, then I can go to the other peaks and try to approximate their intensity or quantity. For example, here, the purple one is the suggested. The black line is my spectra. As you see, the suggested is way more, is quite a bit higher than what I actually have. So I really want to take that into account. because if not, when I do my calculations later on, my quantities may be off. So you need to go to each peak and try to balance everything. Of course, it gets complicated when the black line there's my butyrate peak, but also I have other peaks here. I have caprylet and I have valerate in the same region. So all of them together add to what the black peak is. So I have to go back and forth, adjusting, balancing, playing around to try to see what's the most logical or what makes sense the most. Sometimes when you're not sure, it's the best guess that you can. Later on, when you do statistical analysis and all that, you're gonna take into account your potential error in all these things and how trustworthy your data may be or not. It's not 100% trustworthy. Your quantification may not be exact, but you can be pretty sure that butyrate is there. And also you can be pretty sure that even though you don't know its specific quantity, given other compounds, for example methanol, which only had one peak, you can get an idea of what the proportion is of, let's say, butyrate to methanol. That may be important in your study, it may not, but it is an important thing to keep in mind. There are hundreds of compounds in this database. You can also input new ones. This one, for example, was done for a pH 7.4 because it came from the human body, and we know that these samples tend to be around that pH. However, you may have a plant sample or something else, and the extraction solvent may have been at a different pH. You can adjust that here because, for example, methanol, we saw it in one location, but at a different pH, methanol may actually be further shifted to the left, which is downfield, or to the right, upfield. So all things are things you have to keep in mind when finding potential compounds and adjusting the spectra. There may be shifts due to pH and to other substances in here. Also, if the patient in this case was taking antibiotics or some other medication, that may also cause some things. For example, in this specific sample, actually, you see this very big peak here.
Yeah.
That we still don't know what it is, but we know that these patients were taking some sort of medication, and that may be the actual signature of that, because it's not a sample that we have in our database, so we need to figure out what it may be. You can use databases like this. You can also, there's a whole area of trying to measure how many peaks and the distance between them, and trying to see if that's like a typical peak for not just the molecule, not just, let's say, butyrate, but let's say a methyl group, a CH3, or a hydroxyl group. Each one give different signals, and by the size and the number of peaks, sometimes you can tell not just that there was a methyl group, but how many there were.
Yeah.
And who the neighbor may be. It is a lot of chemistry, there's a lot of uncertainty involved, and it takes a lot of time. But as everything, there are different steps. You first start with what you can easily assign and like you're very sure about. Like I showed you methanol. One peak, it's quite easy to say.
Yeah.
But there are other substances, other molecules, other compounds that may not be as clear. And you have several ways of doing this. You can look for other databases. You can look in the literature. Maybe you'll find a spectra that they were able to identify that peak in question. You can also use standards. For example, here we could ask the medical staff what medication they took. Then we could get a look at that medication and see what compounds it has in them and what characteristics it may have. Maybe it had a lot of nitrogens, maybe it had a lot of other elements, which may give a typical, a signal typical to that. So that's just in a little bit of what this process entails. So basically, in summary, the NMR machine, a big magnet, your sample goes in there. What do you get out from that? You get a spectrum. The spectrum, you have to quality control the spectrum. You also have to process it. You have to make sure that your reference is set correctly, that your reference was a quality reference. So, because if your reference is not good, then the rest is not going to be good. So once your reference is good, you try to align the spectra so it's even. You try to adjust the baseline. Once that's ready, you can bring it into a software like this, and from the database, a lot of the database was already existed from other studies, but also some of them are compounds that we have added ourselves here. And you try to match, and this will give you a good characteristic of this sample. And how is this important? For example, let's say you were studying people, a group of people who are healthy compared to a group of people who have IBD, irritable bowel syndrome. And after seeing so many samples, let's say you were able to sample 100 people, 50 healthy, 50 not, you notice that some compound, let's say methanol and acetate tend to be higher in the sick individuals. You would of course do statistical analysis, but then you would try to see, well, maybe that's a good marker for that disease. If there's higher methanol, maybe it means that this person has this condition, or vice versa. And also you would then try to look at the biochemical pathways, trying to see how is methanol produced, what other mechanism could have produced higher methanol. And then that's where all this comes in, which is what what we do
Yeah.
day in and day out, and it's those big questions and trying to find the answers to these questions, to these diseases, and hopefully from that get more information and maybe get a good idea of what it is that's causing a higher than normal or a lower than normal concentration of a compound in a sample.
Perfect. Can you please explain a few things? For example, this one. Why is this peak down?
Why is that peak down? That's actually on purpose. As you know, most of us and most everything, a lot of substances, the main element is compound is water.
Yeah.
Of course, water is something we don't really wanna. Usually, we're not interested in these compounds. When I ran my sample through the NMR machine, the first sample I run before I run the rest of my samples is one which we call the water suppression sample. And what we do there is try to find where the water signal is, so we can try to suppress it. So like that, it distorts our spectra the least, because since water tends to be the most abundant compound in a sample, usually it would tend to be the biggest signal. And if a lot of energy goes into, if a lot of the spectra is used for the water peak, then all the other compounds will be like much less visible, which would make our job harder. So what we do in that first step is try to find where the water suppression region may be, and we set that number, and each subsequent sample takes into account that in this region is the water region, so we want to suppress that region. And the result is, in this case, that many times you end up with this. The water regions tends to be an upside down peak.
Yeah, so we can say this is water.
Yes. Yeah, that's what it is. And usually your region, the water region, and a little bit upfill and downfill tends to be not very reliable. So this area usually is very unreliable, more reliable here and more reliable here. But that's all part of fixing the spectra, taking also into account where the water region may be and how well it was suppressed or not.
The next thing, these triangles, just like these peaks.
Yeah, those peaks, and they're also a good clue. And I remember I mentioned pH earlier. For example, in this, you see the purple, that's the suggested, right, of where it may be. Let's say this one, there's something that looks a lot like it, let's say to the left. But see, suddenly that little triangle turned red. That's just like warning me that you are outside the pH in which that peak is usually found. And then it would depend on you if it's like a warning saying, okay, just like careful, that's outside the normal pH for that peak. You know your data better, your data best, so it may be that in this case it's outside the normal pH range for that peak, but it may not. But it's kind of like a warning for you to watch out. If you decide to do this, keep that in mind, that it's outside the pH, and if it is your compound, then you may have to answer later on why is it outside the pH, which is also important to know. Because like that we may know that, oh, okay, then in this spectra everything seems to be shifted to the left. Or maybe the pH ended up being lower than we actually thought. So maybe something is acidifying the sample, something we haven't identified. So that's why that's important. It's kind of a warning to tell you it's outside what would be expected.
Okay, so perfect. Thank you very much.
You're welcome, and I hope that was helpful. I know that was a lot, but feel free to always come around here to ask us any questions about this. And as you know, it's a process, so there are a lot of steps, and it's a continual learning process, and also learning from mistakes and then modifying things and fine-tuning to try to make the best assignment in this case and quantification of compounds.
So
That's
perfect.
it. Hopefully that was good for you.